Welcome to the MR lecture on methods of carbon-13 detection, both direct and indirect. Carbon-13 detection can be used to um, examine the very small, typically natural abundance signal of the stable isotope carbon-13, with the advantage that it has very high spectral resolution. Um, More commonly, it is used to track metabolism, either to find relative rates of metabolism or absolute rates in the case of kinetic studies, where we supply a substrate chemical that whose carbons are enriched with carbon-13, well above the 1% natural abundance. And then we can track the appearance of those carbons in metabolic products of the substrate. So this lecture will cover the various ways that the detection can be done with magnetic resonance spectroscopy. Uh, these methods can be applied in vivo. We will start with direct detection because they can be broken down into uh, approaches that observe carbon-13 itself or approaches that observe protons, hydrogen, that is coupled to carbon-13, or hybrids in between that manipulate the magnetization um, between proton and carbon. So carbon-13 direct detection is the simplest. It's just often consists of pulse acquire experiments. And without any localization, you get a lot of contribution from whatever is in the sensitive volume of the detector. And these are spectra from a rat brain in 1992. And these are spectra from a rat brain from 1992. At the top, you can see C13 glucose, the beta and the alpha anomers. Recall that glucose, when it's in solution, equilibrates between the chair and the boat forms. One dominates. So here you have two peaks representing the C13 glucose signal. And that appears in the brain because in this case, the rat was infused with carbon-13 labeled glucose. There's a very large lipid peak here from outside of the brain. These, as the title says, this is not localized. On these parts per million, notice that there's a very wide dispersion of parts per million. These spectra were conducted with a resonance frequency for protons of 360 megahertz. For carbon-13 was about 90 megahertz. So every ppm represents 90 hertz. So this is a very wide span, and we can detect this region or we can detect that region. We were not able to detect everything at the same time. And we also use something called decoupling, which we'll talk about later. So first we focused on this, and then we focused on this. And we can see lactate for this region. This is postmortem, so the brain converts glycogen and glucose to lactate within seconds after blood flow is stopped. And there's glutamate and glutamine and aspartate. And note that how it's not so hard to quantify this glucose peak because we could just draw a baseline here and measure these peaks. But it's difficult here to know exactly where the lipid stops and the small molecules that interest us begin. Localization would be very beneficial. So this is also direct detection. It was done also with pulse acquire. What makes this different is that ISIS localization was used. So remember, ISIS uses selective inversions applied in combinations, in different orientations, X, Y, and Z, to form a box. So for a 3D box, we need eight acquisitions, and we repeat that process over and over until we have enough signal averaging to get a nice spectrum. And here we have, we can see the metabolites with, there's a very, very broad contribution from lipids and a little bit sharper here, breaking through. But it's much, much clearer than we had over here. The vast majority of this lipid peak is now gone because of the localization, and it's easy to quantify glutamate, glutamine, different carbon-3, carbon-4 of these different molecules. So this spectrum shows 60 minutes of accumulation in 144 cubic centimeters of brain. That's a pretty big piece of the brain. So this approach is useful for studying global processes that are spatially diffuse rather than very small localized regions of the brain. Now there is a limitation with this, as with everything. This spectrum was acquired at 2.1 Tesla. There is a 53 Hertz difference between glutamine C4 and glutamate C4 at this field strength. These peaks are separated by frequencies in Hertz. Now, when we're doing localization, we select a band, we put on a gradient and select a band of frequencies for the inversion. So now we have frequencies selecting location and frequency selecting spectra, and that creates a confound. The volume of glutamate carbon-4 may be located here, but glutamine carbon-4 is going to come from a slightly different location in space, and this is called chemical shift dispersion artifact. So if the volume is very large compared to the dispersion artifact, it doesn't matter much. But that's not always easy to achieve. And to minimize it, typically what we do is make the gradient strength high. So that's big compared to the frequency shifts among the chemicals. The gradient strength is high, and when the gradient strength is high, we need broad bandwidth pulses. To have a broad bandwidth inversion pulse, the pulse has to be short in duration. And if it's short in duration, it has to be powerful to achieve a tip, the proper tip of 180 degrees for the ISIS. So to overcome the chemical shift dispersion error with this approach takes more radio frequency power, and we have limits on that with what we can apply safely. So this worked well for the time, but it's possible to do better. So we'll look next at how do we compare the sensitivities of carbon-13 and proton? Remember that the net magnetization is proportional to gamma times B0. So if you do an experiment with carbon-13 or protons at a particular frequency or at a particular magnetic field strength, you have the same B0. What's different is the gamma. Protons have a higher gyromagnetic ratio than carbon-13, therefore they have greater net magnetization. So protons are more sensitive than carbon-13. And here, show me this and this. There are other factors that come into this as well. So the signal to noise overall is proportional to 5/2 the power of the gyromagnetic ratio. Now at the top, we have a proton signal. Suppose we have carbon-13 labeled lactate, in this case, 1.3 parts per million. The carbon-13 splits what would normally be narrower peaks into two separate peaks. Here's the lactate one. So now to improve our ability to localize and the sensitivity, we have an option to exploit the frequency differences between carbon-13 and protons. At the right here, we have a lactate molecule. Notice that one of the carbons, the yellow one is designated as carbon-13. It's a methyl group. It's in a methyl group, and it has 3 protons on it. If you were to take a spectrum of that at high field strength, you'd see 2 peaks centered around 1.3 parts per million in the proton spectrum. If there were no carbon-13, you would have just 1 peak in the middle. And we're going to assign it a total area of 3 because there are 3 protons. Protons have a high gyromagnetic ratio compared to carbon-13. So here the signal to noise for direct detection with a pulse acquire experiment for proton is proportional to the gyromagnetic ratio raised to the power of 5/2, multiplied by a factor to deal with the T1 saturation. That is, a note that if you have a very short T1 and you tip 90 degrees every time, you will rapidly eliminate your Z magnetization and you won't see much. If you go out to long T1s, we'll look at the extreme case, TR, a repetition time of infinity. So you get full T1 recovery between every acquisition. And we have this big factor then of gamma to the 5/2. Now we'll look at the same experiment with pulse acquire for carbon-13. What would be a single carbon-13 peak, if it had no coupling, is now split into a quartet by these 3 protons. And that splitting occurs according to whether you have all the protons have their nuclei with spin up, or one of them was with spin down, maybe this one, or that one, or that one, or 2 of them in any combination may be spin down, or if they're all spin down. And each one of those creates a slightly different environment, an interaction with carbon-13. So they're split into 4 peaks. And notice that the total area of these peaks, instead of being 3, it's 1, because there's only 1 carbon-13. Here you had 3 protons, but here there's only 1 carbon-13. So they're down by a factor of 3 simply because of the number of nuclei available. Another difference is now the gamma raised to the 5/2. The gamma of carbon-13 is about 1/4 that of protons. So this factor is much less. And here is the same T1 factor. And down here we have the gyromagnetic ratio presented in radians per second per Gauss. This, remember, is equivalent to 42.57 megahertz per Tesla. They're just different ways of expressing the same number, but the point is that this number is much bigger than that number. So if you factor in all these cases for lactate, all these factors, you find that the signal to noise for a single scan for proton pulse acquire versus carbon-13 pulse acquire is about 100 to 3.2. So protons could give us a significant sensitivity boost if we could exploit it somehow. We'll move next to NOE, nuclear Overhauser enhancement. We will be detecting carbon-13 in this case, but using the protons to boost sensitivity. So here we have, on the right, we have yellow O's that represent carbon-13 nuclei, and white O's that represent protons or hydrogen nuclei. If we irradiate the protons, we can gradually equilibrate their distribution between high and low energy states. We do this until we reach saturation. Once it's equilibrated, we can't do any more. We're not going to actually reverse it. Then we allow some relaxation to occur. And when this occurs, we end up actually transferring um, the magnetization, enhancing the magnetization on the carbon-13 side. We get a larger difference between the energy states on the carbon-13 side. And then when we acquire, we have boosted the signal. Now to achieve this, the T1 relaxation has to be dominated by dipolar interaction. That is, if these interactions are dominating the relaxation, that means that they are interacting. They are the effective interaction. If something else is driving the T1 relaxation, then we're not going to have such efficient transfer. If we look at the lactate example again, we go to 21 parts per million. That's where the lactate resonates in the carbon-13 spectrum. It's a pulse acquire experiment. It's the same thing you saw before. But now we do proton irradiation ahead of the 90-degree pulse. Now there's some of the same features of the same experiment, of the pulse acquire experiment, are here, but there's a boost due to the nuclear Oberhauser enhancement. If we didn't do anything, we would just have 1. But now we add a factor of the ratio of the gyromagnetic ratios divided by 2. So half of gamma of protons divided by gamma of carbon-13. And that can give an important boost to the signal. So now, instead of an integral of 1, we can be up to an integral of 3 by transferring energy, the polarization from the protons, which have more of it, into the carbon-13. It's not as sensitive as if we looked at the protons directly, but it is a major enhancement. Another approach is the polarization transfer. Again, we are observing carbon-13, but we are exploiting the higher polarization, the higher net magnetization that is present in protons to boost the sensitivity of our carbon-13 measurements. So as discussed a moment ago, the proton spectroscopy is more sensitive per atom than carbon-13. And polarization transfer allows us to move some of the proton polarization to the coupled C13 nuclei. Now at the moment this sounds like the NOE that we just went over, but it's a different procedure. In this procedure, we start with an excitation pulse. It looks like a pulse acquire experiment. There's just a 90-degree pulse at the beginning, and nothing happens on carbon-13. We wait some time. While we are waiting, there's an opportunity for the carbon-13, which has not been perturbed, but for that carbon-13 to interact with the protons. The J coupling will cause, because we end up with 2 peaks, there's some kind of interaction happening between them. If then we flip 180 degrees, we wait again, we flip 90 degrees, we wait again. We can, if we carry out this procedure, we can transfer magnetization from the proton side over to the carbon-13. We need some kind of a double transmit available and a multi-nuclear capability on the scanner. We have to be able to transmit to protons and also to carbon-13 within the same sequence. And it can be done through one coil, or it could be done through a combination of coils that as a unit can transmit and receive proton and carbon-13 frequencies. And one of the items that this sequence not only allows us to boost the sensitivity of our carbon-13 detection, it also allows us to do localization in the proton domain. The proton domain has much smaller chemical shift dispersion. So the confound between the localization and the chemical and the location of different chemicals in the spectrum is much less severe than it is typically for carbon-13. The way this sequence works, we start out with everything relaxed. Carbon-13 and proton. We have so carbon-13 here on the left and protons on the right. Before we do anything, we have Z magnetization, and note that the Uh, net magnetization for carbon-13 is less than that for proton. We do a pulse acquire. We do an excitation pulse just in the proton domain, so only that channel has been activated. And here, nothing's happened to the carbon-13, but the protons are now in the XY plane. Now we wait some time, and we still haven't touched the carbon-13, so there the net magnetization remains undisturbed. But just as we get different peaks, say if we have two peaks, to one carbon-13 or coupled to one proton, then that one proton will end up, half the protons will drive half the vector in one direction of rotation, and the other half will drive it in the other rotation. The frequency difference between them is called the J coupling constant. I just repeated that frame here, and now we go to the next step, highlighted in white here. It's 180-degree pulses on both channels at the same time. And so we end up flipping the carbon-13 from up to down. The net magnetization has just moved to down. If we were to open the receiver here, we wouldn't detect it because it's not in Z. It's not in X, Y. It's in Z. And here we have moved these so they flip them. And then by flipping this, we've actually continued to make the vectors drive in the same direction. They're still driving apart. So we flipped this. By flipping this, we've caused the net magnetization to continue to separate here. Our goal actually is to wait during this next time delay for them to go completely opposite. If we were to open the receiver here, as long as we had sufficient spectral resolution, we'd see two peaks, one up and one down. And we wouldn't see anything in the carbon-13 side. And that may seem strange. What to put the magnetization in a state where it's not very well detected. If the shimming's poor, if we don't have the resolution, the up and the down will cancel each other and we'll see nothing. But what's important to note is that by letting these, under the influence of the carbon-13, by letting these process completely opposite to one another, we've maximized the evidence of their interaction. So we'll go to the next pulse. And this is kind of, you can think of this is where the magic happens. By flipping 90 degrees, we take these anti-phase this anti-phase magnetization and move it to Z. And that doesn't really matter to us because we're not detecting, remember this is a proton side, we're not detecting protons, we're detecting carbon-13. Now at the same time we get this transfer, it's called a double quantum coherence, and it gets transferred to the carbon-13 when we make this maneuver. So we're moving the polarization from proton to carbon-13. And because there was a 90-degree pulse, we would have a small carbon-13 signal here. I'll leave it drawn through the rest of the sequence, but in reality, we're putting gradients in and eliminate that. Okay. And now we wait another time delay. And the whole point of the rest of the sequence is to refocus this anti-phase magnetization in the carbon-13 along one vector in the XY plane so we can detect it with more sensitivity. When we flip 180 degrees, we flip both nuclei 180 degrees. So the Z would be antiphase, but some of it's up, some of it's down. It's in Z. And these continue to process toward one another. If we wait the right length of time after that, they come back into phase. They have phase coherence. We can open the receiver and detect a carbon-13 signal. So in this sequence, the first thing we do is we set this up so that with a 90-degree pulse to protons, so that the carbon-13 influence has a chance to make itself known during this time delay. We bring 180-degree pulses in here so that the dephasing can move to opposite and really reach full magnetization, full antiphase magnetization. Then the rest of this is designed to, the 90s, transfer the polarization from protons to carbon-13, and the rest of the sequence is designed to bring the carbon-13 into phase coherence. So this was, you can think of this as the central point. This sets up, prepares the system for transfer, this makes the transfer, and this brings everything back together for the carbon-13. Here is a video of this playing out. 90-degree pulse in protons, and then get some dephasing. You wait the right length of time and then flip both things 180 degrees, and they continue to dephase. Now is the moment when the transfer occurs. We have 90-degree pulses in both channels, and we start to bring things back together. There we go. We'll bring everything back into phase coherence on the carbon-13 side. Now, this is 4 Tesla compared to 2.1 Tesla that I showed you before. So it's about double the net magnetization. We get a boost in sensitivity there. Note that the baseline is cleaner, so the localization is better. We don't have this broad hump underneath. This is only 30 minutes of accumulation compared to an hour of accumulation that I showed you before, and it's only 90 cc's compared to 140 cc's. So the sensitivity is there's multiple aspects where we can use the sensitivity. It's much better with this polarization transfer compared to the carbon-13 direct detection. But again, we see C13 glucose infusion during this while this is running. We see glutamate carbon-4, glutamine carbon-3. So to summarize, just for the polarization transfer, most of the signal is actually coming from protons, even though we're looking at carbon-13. Because of that, we can perform the localization in the proton domain where the chemical shifts are squeezed together more tightly. That means whatever frequency dispersion we have across space can dominate versus the smaller frequency dispersions that happen within the spectrum. That reduces the required gradient strengths, the radio frequency power levels we need, and it reduces chemical shift displacement errors. Now, if we just do that, we're still going to have some difficulty seeing it, because to be fair, the spectrum I showed you before wasn't just with polarization transfer. We were also using decoupling. In some of the examples we've shown you, the carbon-13 peaks are split into 4 by the protons, or the proton peaks are split into 2 by the single carbon-13 nucleus that they're coupled to. And we can negate that splitting by using something called decoupling. The splitting is due to coupling, so this is called decoupling. We come back again to the favorite molecule for today, carbon-13 labeled lactate. In the proton spectrum, we see 2 peaks at 1.33 parts per million. There are 2 peaks, so each one has half the height of the original. If you decouple perfectly, you get 1 peak with full height. It's easier to measure this, especially when you consider that there will be noise around this. If you have a small plant sticking up in a field of grass, it's easier to measure the plant if it's taller. Now, if we look at carbon-13, we have each of these peaks is 1/8. Well, actually, now if we look at carbon-13, the peaks are even a smaller component of the total because we have peaks split into 4. And if we decouple them, now we have 1 peak of greater height. Notice that we're starting out with smaller heights overall because we only have 1 carbon-13 versus 3 protons. But still, we're better off It's easier to measure one peak in the carbon-13 spectrum than it is to measure this broad series of small peaks. Now, how do we manage to collapse those peaks as multiplets into one? Well, here, if we want to observe the carbon-13 spectrum, so each dot may be one observation, and we decouple protons, what we do with one approach is continuous wave decoupling, where we're applying magnetization to these protons that are coupled to the carbon-13. We're applying radio frequency to these protons. The effect is to prevent them from settling into an up or a down influence on the carbon-13. And they end up averaged. They have an average location, and that is an average orientation in the middle, neither up or down. And so the carbon-13 spectrum ends up giving us just one peak. This actually works effectively. You have to keep the power very low so that you don't deposit too much energy. But a significant downside is that it has an optimum, a very narrow optimum for activity. Because remember, a very long pulse has very high frequency selectivity. And so when we get off resonance, we're not going to be decoupling any more than maybe one of the chemicals that we want to observe. So then there's broadband decoupling. I'd like to highlight these slides are from Robin de Graaf. So here is the same carbon-13 FID, and now we apply a series of discrete pulses with appropriate, these are 180 degrees and appropriate spacings and durations. And that will work, and you can make it broadbanded. But it takes a lot of power, and we get a lot of tissue heating. So that doesn't work so well in vivo. So broadband decoupling uses composite pulses. Composite pulses are groupings of hard pulses, just like the 1-1 bar example that we discussed in another lecture for water suppression. Well, this is a set of hard pulses put together, very particular pulse angles and timings to achieve this randomization of the apparent randomization of the proton nuclear spins being in the up or down orientation. This is all can also be done with adiabatic pulses. So we want a dwell time. So we want the decoupling scheme can span over several dwell times. Dwell time is how long it takes to get each point in the channel that you're observing. So the carbon-13 is what we're observing in this example. The time between each dot is their dwell time. And we want the decoupling scheme to cover, it can cover several of these dwell times. And it is possible by doing this to achieve broadband decoupling at power levels that are acceptable and safe in vivo. We still have to watch the limits carefully, but it can be done effectively. The goal is to get us to, this is our observable. Notice that for just sort of general, when you open the receiver, if you don't do any decoupling, you get movement, precession of the magnetization and splitting up with this, governed by this J coupling constant J. We want to have that. Very effective decoupling would be to collapse this observable component to 0.98 of the 98% of the magnetization. That would get us almost all of our signal collapsed into a single peak. This other term, IYSZ, that is the formal representation of the double quantum state of the magnetization being antiphase due to the J coupling. So we want to see an in-phase component, not an antiphase, and we want it to stay in phase the entire time we're observing it. What I've described is perfect decoupling. Instead of having two off-resonance peaks oscillating around the rotating frame or the ideal Larmor frequency, we have just one nice peak in the middle. And that's what this representation would be. Here are two uncoupled peaks. I mean, these are two coupled peaks. And with decoupling, they collapse into just one. What's more realistic, nothing's perfect, is a spectrum like this, which translate into a spectrum that's mostly decoupled, but it has some remnants off to the sides. These are called decoupling sidebands or cycling sidebands. So the decoupling cycle span can cover several dwell times, but it does have to be kept short relative to 1 over J. So in the case of carbon-13 and proton, J can be maybe 120 hertz. 1 over J then is just a few milliseconds. So the decoupling cycle has to be brief, briefer than these several millisecond precession times. The decoupling scheme, to be useful, has to give us broadband decoupling. So we want to cover a broad spectral width. If we could get the entire frequency width band, that would be 100 parts per million. If we can't do that, we do the best we can and make sure it covers the metabolites that are of primary interest to us. And we have to keep low peak power and average power as a matter of safety. So continuous wave decoupling is not so good because it's very narrow band. We can't make it broad enough banded without increasing the power to unacceptable levels. Broadband decoupling, there are many different schemes to achieve it, and they are designed to maintain low peak powers and average powers and still hit a good range of metabolites. So far, we've talked about ways to detect carbon-13 itself. Can either do this without localization or improve it by adding localization. We can boost the sensitivity with the nuclear Oberhauser enhancement. We can boost the sensitivity further if we use polarization transfer. And we can make the spectra easier to measure and improve the sensitivity of the signal noise for any given peak by decoupling. Now there's another realm where we can go with a tremendous boost in sensitivity, and that is proton-observed carbon-edited spectroscopy, POCE. So instead of transferring polarization from protons to carbon-13 to make the carbon-13 more sensitive, now we just go straight to the protons. We're still exploiting the J coupling between the protons and the carbon-13, but we're observing the protons themselves. So it's a method of heteronuclear editing. In another lecture, we discuss homonuclear editing, say for detecting lactate or GABA. This follows the same principles, but it's heteronuclear. So we are perturbing carbon-13 and looking at protons. The direct proton detection is much more sensitive on a per atom basis than carbon-13. Remember that gyromagnetic ratio raised to the 5/2? Well, that's much larger for protons than it is for carbon-13. And the polarization transfer, as good as it doesn't match the direct detection and sensitivity. And we still can do our localization in the proton domain. So we cut down on the chemical shift dispersion artifacts. The way this sequence works is people need to be still for pairs of acquisitions. We need two sets of acquisitions for the carbon-13 detection. In one of them, we have a plane spin echo, 90, 180, and this can be adapted to various pulse sequences, but as most basic, we have a plane spin echo sequence. And if we do that, we'll look at protons that are coupled to carbon-13 and protons that are not. At the beginning, before we've done anything, everything is sitting along the z-axis. We do a 90-degree pulse, and we see everything is tipped into the XY plane. It doesn't make any difference whether they're proton coupled or carbon-13 coupled or not. Now, if we set this time delay, T1/2, to just the right length, we end up with that antiphase magnetization. This is something that you saw in the polarization transfer. What is the portion of the protons that are coupled to carbon-13? Half of them will precess one direction relative to a rotating frame, and half will precess the other direction. 180 degrees out of phase if we wait just the right length of time. What's coupled to carbon-12, what's linked to carbon-12, experiences no J coupling, and it just remains where it is in the rotating frame. Then we do the next part of the spin echo, and we flip, depending on the orientation we set this, we can flip the magnetization around the x-axis. So this dark orange now moves to the opposite side, and the light color moves over to this side. And because it's a spin echo and these time delays are balanced, the length of time it took them to become antiphase now is the same length of time it takes them to come back into phase. And here we go. So if you were to do this experiment, just this experiment, you wouldn't be able to tell what was coupled or uncoupled, except if you applied decoupling, you would just see one peak at the end. It would look the same as if you had done unlabeled material. You actually would see some splitting if you didn't do any decoupling, but the full magnetization comes to you, and just like in a normal phase, whether it's coupled or uncoupled. Then we do another acquisition. It's also spin echo, but it's a little different because we apply a 180 degree pulse on the carbon-13 during the spin echo. And now we start out the same. We tip the coupled and uncoupled magnetizations 90 degrees. Here they are together, just the same. Here they dephase, just the same. They go to antiphase position. And now we flip not just the proton, but the carbon-13 also. When we flip the carbon-13, that causes whatever was rotating, this orange vector was rotating this direction, clockwise. Well, we flip the carbon-13 and we cause it to rotate counterclockwise. This one was going counterclockwise. We flip the carbon-13 and now it's going counterclockwise. And that brings them back to phase on the opposite side of the uncoupled spins. If we take the two acquisitions, the one without the carbon-13 inversion and the one with the carbon-13 inversion, we subtract them, the green vector, the uncoupled spins, disappear. They cancel. So any protons linked to carbon-12 are eliminated with the subtraction. And for the carbon-13, we end up with twice the magnetization of the one vector that's double the carbon-13 signal. So that's not an enhancement of signal in the protons. We have two acquisitions and we have twice the signal because there are two acquisitions. But the advantage was that we eliminated the carbon-12. Here's an example from the brain in vivo. Now this is 5 minutes of accumulation in a volume of only 22 cc's. And it is possible to do better than that. So here is the total spectrum, C12 plus C13. Here is the spectrum with the C13 inversion applied. So now it's the total minus the C13. And because so the glutamate peak is smaller. And then when we take the difference, we have a glutamate peak. Now this difference actually is smaller. You can see that if you subtract this peak from that peak, you get a very small difference. So we scaled it up by a factor of 4 to show it here. The N-acetyl aspartate turns over very slowly during the C13 glucose infusions. So N-acetyl aspartate has basically no labeling in it, and it subtracts to 0. The 1% is too small to detect in this short time and this small volume. Creatine and choline also Now, it looks like you might say, oh, there must be labeling here, but actually this is subtraction error because it's crucial that people hold still with this measurement. We're looking for a very small difference in the signal, maybe representing 10 or 20% of the size of a peak. And if they move a little bit, we can get errors. In this case, the person moved and the choline and a little bit of creatine showed up. So the advantages of this are that it's very highly sensitive because now we're looking at protons. And we can measure the percent enrichment, not just the amount of carbon-13. So we can say, oh, this peak represents a certain fraction of the total glutamate. And we can get finer spatial resolution because there's greater sensitivity, or finer temporal resolution. There's some disadvantages that are significant are that it's more sensitive to subject motion than some of the direct detection that we do. And I haven't mentioned this yet, but we're limited in the variety of chemical species we can study, especially in humans. The glutamate and glutamine are both present here, but we have to, because we're applying a radio frequency pulse in the carbon-13 domain and we are decoupling in the carbon-13 domain, our bandwidth to apply it safely in vivo is limited. So in the end, we were only able to look at the protons connected to glutamate carbon-4. So this is ideal. This approach is ideal for cases in which you want a more highly specific regional information. But it is acceptable not to measure as many metabolites as you would otherwise want to. And the spatial resolution is high enough that we can actually do gray and white comparisons now. With the 140 cc volume or 90 cc volume, that would be very difficult. With a 20 cc volume or 22 cc volume, we can now look at regions of mostly gray matter. This was about 60% gray matter and mostly white matter. This was about 60% gray matter. This was about 60% white matter. And by analyzing these both together, we found that gray matter has about 5 times the TCA cycle rate. That's where the intermediary metabolism closely related to oxidation. It is oxidation of substrates, and then it's linked to oxidative phosphorylation to make ATP. So this is about 5 times as fast as the same process in white matter, which is similar to what high-resolution PET has shown. Now we move to another level of regional specificity that is made possible by the POCE approach. Iced Pepsi the name comes from in vivo carbon edited detection with proton echoplanar spectroscopic imaging. So echoplanar imaging, you use it for functional imaging. It's a very fast way to cover K-space and get images quickly. You can do also spectroscopic imaging, mapping of chemicals with echoplanar spectroscopic imaging. And you can do that in the proton domain. If you acquire pairs of proton spectroscopic images with and without carbon-13 inversion pulses, you can do mapping of POCE, of the C13 seen through protons. So we combine POCE and echoplanar spectroscopic imaging. You take pairs of the echoplanar spectroscopic images with and without the C13 inversion pulse, take the difference between your maps, and what you'll see are carbon-13 labeled metabolites. And if you infuse carbon-13 labeled, say, glucose over time, you can watch those maps develop intensity. We can analyze those maps then to determine metabolic rates. So this is from a paper published by Famid Haider in the Yale MR Center back in 1999. He has an outline of the rat brain, cross section, and the echoplanar spectroscopic image over that brain. And he zooms in. This around here, we have glutamate and glutamine, C4, and C3 in the proton spectrum. And it's dominated by glutamate. He performed those over time during C13 studies, and we can see differences between gray matter and white matter, and then there are voxels in between. Actually, the purpose of his study was to look at volumes of stimulated gray matter and not stimulated gray matter. This was, I believe, with whisker barrel brushing, where the sensory cortex showed a much higher activation, showed a lot of metabolism in response to that elevated function. So the POCE and the PEPSI was ideal for this application because in Famid's study, he needed high spatial resolution to differentiate resting and activated areas of the brain. In summary, direct C13 detection gives us more precise results when labeling localization is used. Remember how we got rid of that broad lipid lump once we went to localized spectra? But there were still some issues with the voxel locations for different chemicals, the chemical shift dispersion artifact. So the sensitivity and the spatial localization of C13 detection can be improved if we use polarization transfer. NOE helps, but this goes even further, and the localization advantage is a very important factor. And we can do even better with sensitivity and localization if we go to an indirect detection method like POCE, proton observe, carbon edit. Downsides of this are that people have to hold very still. We need cooperative subjects and people coaching. I recommend when you prepare someone for a scan and tell them they need to hold still, it can be helpful to tell them what you mean by that. I've had people swear they're holding still and they're in there wiggling their feet, but they think they're still. For these, for some of our studies, I tell them that if they move even as much as a width of a pencil lead, it will disrupt the scan, and it helps. It's very important to have people situated comfortably with padding that is firm enough to help hold them in position so they can relax, but not so firm that they feel frozen. We also lose chemical variety with POCE. We can't see as many chemicals as we could have if we were doing carbon-13 spectroscopy, but depending on your application, it can be worth the sacrifice. The POCE can be combined with rapid spectroscopic imaging methods like echoplanar spectroscopic imaging to get images, maps of carbon-13 turnover. And the maps are useful when you want to evaluate tissue-specific metabolism, certain kinds of tissue or brain regions, or look at regional metabolic differences, say with function or disease. That concludes the lecture on carbon-13 detection.